Here's the solution to problem 13 from section 8.4. This is similar to the problem that we were doing at the end of class on Tuesday. The idea here is to estimate the value of a series, an infinite series of numbers, but to be able to control the error that we make. In other words, we want to make an estimate, and then we want to be able to say for sure how close our estimate is, even though we don't know what the exact answer is. So the form of this will be an estimate that will be an initial part of the series. So we'll take an initial part of the series, and then what we're going to refer to as the remainder is all the rest. So what I circled in blue, or put a blue box around, that's my estimate on the left, and then on the right, inside the red box, are all the rest of the terms. So notice in the red is an infinite number of terms. So that's another series in itself. But that's what we consider the remainder. So we have our estimate on the left and our remainder on the right. The reason that we can give bounds on the remainder is because we know how the remainder is related to integrals. And right now, that's the only thing that we know that we can compare series to. In the next section, we'll see that there are other things that we can compare these remainders to. But what we saw today was we can make a comparison between an integral and a series by drawing pictures of their area. If we have a picture of the area for an integral, then we can relate that to the left or right sum, the left or right Riemann sum, as long as we make the Riemann sum have rectangles that have a base of 1 and have their sides always at whole number values. So the picture we drew in class today showed that there was, for the stuff that's in red, there was a lower bound. The lower bound for this, I didn't mean to use red, hang on. The lower bound over here, I'll call it LB. So this is a number that's definitely smaller than what I put in the red box, is going to be the integral from n plus 1 to infinity of 1 over x to the 6th dx. If you draw the area represented by that integral, and you put, let me think, left-hand rectangles under it, each with base width 1, then you'll see that what's in the box has to be bigger than the integral. On the other hand, we know that if we integrate from n to infinity instead of n plus 1 to infinity, then again, if I draw what that looks like, that's more like the picture I had in class, drawing this picture and putting right-hand rectangles, each with base width 1, underneath it, we'll get these terms. And so the stuff in the red box has to be in between these two values. And so we consider this the the lower bound of this remainder, and this guy's the upper bound for this remainder. And in both cases, I can do the calculus because it's a fairly simple integration. So what I get in this integral, I'll just write it down here, but what we should get is 1 over 5n for this guy. I'm sorry, 1 over 5n to the 5th for this guy, and 1 over 5n plus 1 to the 5th for this guy. That's just doing the antiderivative of x to the minus 6th being minus 1/5 x to the minus 5 evaluated between infinity and n, or evaluated between n plus 1 and infinity on this side. But those are what those values will be. And so now I can actually answer all of these questions. And there's nothing special about this particular function. Anything that you can integrate, we can get these upper and lower bounds. So for part A, it actually wants the formula in terms of n. So the upper bound for the remainder is yes, go away. The upper bound for the remainder is here. So that's the answer, 1 over 5n to the 5th is the answer to the first part. They're just asking what the upper bound is. If that asked for lower bound, we would use this one. The next part of the problem asks how many terms are needed to ensure that the remainder is less than some value. So that's just asking to figure out how this upper bound can be less than 10 to the minus 3. So I can solve that. 1 over 5 n to the fifth equals 10 to the minus 5. I can solve this for n. Let me rewrite it as a fraction. That'll make me feel like my rules are okay. So that's that. You can either think of this as cross multiplying or just taking the reciprocal of both sides, but that'll mean that 5n to the fifth is equal to 10 to the fifth, and that means that n to the fifth is equal to 1/5 10 to the fifth. And I just now realized that I copied this down wrong. All right, so it's asking for 10 to the minus 3, not 10 to the minus 5. So sorry about that. If I go back and revise, so this is 10 to the minus 5, this is a 3, this is a 3, this is a 3. Sorry about that. So I just wrote the problem down wrong. This was my issue. I just copied that wrong. And 1/5 10 cubed. So if I raise both sides to the 1/5 power, n is so 1/5 10 to the third to the 1/5 power. So if I do that, I get approximately 2.885, something like that. But remember, the n here has to be, the n represents how many terms I'm taking. So the n has to be a whole number. So what this answer tells me is that 2 is not enough, but 3 is enough. So I want to just take the first whole number above this number that I got. So 3 will be the correct number of terms here. That's the first value of n that you could have that makes this less than 10 to the minus 3. If you put 2 in here for n, it will not be less than 10 to the minus 3, but if you put 3 in, then it will. And then finally, it asks us for the upper and lower bounds on the exact value. And that just goes back to the original picture. Remember, I said that we start off with the sum 1 over 1 to the 6th plus 1 over 2 to the 6th, and so on, up to 1 over n to the 6th. And then I have plus a bunch of terms that we could think of as the remainder terms. And that's the thing that I stuck in the red box. And I said the upper bound and lower bound were based on the integral. So I said integrating from n plus 1 to infinity of 1 over x to the 6th was the lower bound. And integrating from n to infinity was the upper bound. And we showed that this was 5 over n cubed. And, sorry, 5 over n plus 1 cubed. I was trying to copy down what I had on the first slide. So, and this one is 1 over 5 n cubed. So the answer here is that the the correct value of this sequence, the original thing, the estimate plus the remainder, so this original thing is somewhere between this estimate plus the lower bound and this estimate plus the upper bound. So that's what I'm looking for here, is one that looks like this first partial sum plus this lower bound term and this first term partial sum plus this upper bound term. So if I go down through, that is this one. Right, looks exactly like that. This one's not it because it just has the two backwards, right? They switched the lower and the upper bound. So that shouldn't be too hard to figure out because this is a smaller number than this, right? Bigger denominator is a small number. And this one they just made up. I don't know what they're adding up here, but this is not a partial sum of the original series, right? We want partial sum of the original series plus lower bound and plus the upper bound. So the true value of this series for any particular n will fall between these two guys. And so that's how we're able to use one of these as our estimate, and we know a maximum error that we might make.